So today we'll be designing the half wave and full wave rectifiers, and we'll see how they perform. We'll uh, see their performance. We'll check their performance, whether how far they are successful in converting our a pure AC signal into a signal which has good amount of DC in it. So the output will have some DC. The input was a pure will be a pure AC signal, sinusoidal signal, and at the output of rectifiers will expect a signal which is having some amount of DC. So the AC component at the input will be converted to DC component. So up to how much are these rectifiers uh, good enough to produce output having DC, that we'll see. So we'll judge the rectifiers in terms of their ripple factor and form factor. So we'll see. Let us start our design. So this is our multisim interface. So we'll bring some diodes into our breadboard. What are the popular diodes that is available? What are the popular silicon diodes that are available to us? So this is the way a physical diode how they look like. Okay. Whenever I am getting a diode in my implementation on multisim, it will use the symbol representation of the diode. But you should always know that physically a diode will look somewhat like this. You must have seen diodes in this form in the laboratory, in the basic electronics laboratory, where you must have tried implementing uh, half wave and full wave rectifiers, clippers, and clamper circuits. Okay, you must have seen that diodes look like this. Okay, this is the way a typical diode looks like. Okay. So these are different ways how a physical diode looks like. Okay, this black part is connected to the P side, whereas the silver part, or the grayish part is it gives you the N side. Okay, N terminal. This is P. This is N terminal of the diode. So this is the physical diode, whereas we'll be in our design we'll be referring to a diode in its symbol form. So this is the P terminal and this is the N terminal. So you must be able to relate. Okay, this is the way. So this is what I wanted to tell you. Okay, this is P terminal. This is N terminal. On a physical diode, this is the symbolic representation. This is the physical diode. The actual physical diode looks like this. So the black part gives you the P terminal. The grayish part gives you the N terminal. Okay. Okay, this is a typical specification sheet of a diode, which is 1N4001. So this is how a specification sheet will look like. Okay, this one. This is the specification sheet of 1N4001 to 1N4007. So we'll see whether 1N4001 is available in our library or not. Yeah, it is there. 1N4001G is there. If we bring it to our virtual breadboard, let us see. These are the different specs of this particular diode. So this is IS, the reverse saturation current. This much. This particular diode, that is 1N4001G, has got this much of saturation current. This is the parasitic resistance. So likewise, different specs are given in this table. Where can we find the knee voltage? That is, here it is given, Vj, in the form of Vj, the junction potential. that is given 0.7 volt. That is the knee voltage of this particular diode. 1N4001G is having a knee voltage of 0.7 volt. And at the very start, it has given the saturation current, the reverse saturation current. It is 1.22478 into 10 to the power minus 8. Okay, so it is almost 122 microampere, 122.47 microampere. And you already know that reverse saturation current is in the range of microamperes only. So there are different parameters and the value of those parameters for this particular diode given in this table. So where did I get it? I just double clicked on the particular diode and I went to the edit model. So what the different the model of this diode, or you can say the parameters of this diode, the specs of this diode is given in this table. So anyway, we'll be using this diode to implement a half wave rectifier first of all. So let me get a signal source. So I'll get a source, power source, signal voltage source. What should I get? Signal voltage source. Let me get a signal voltage source. AC voltage source. Okay, I have got a signal voltage source. Under signal voltage source, I got the AC voltage source. This is a sinusoidal source which will give me a 1 kilohertz sinusoidal signal of peak value 1 volt. So I will connect it to this diode in the way we connect for a half wave rectifier. I need a load resistance across which I will be observing my output. So let me get a load resistance. So under the basic group, let me find a resistance. So where is the resistance? Here is the resistance. So any value of resistance I can choose, and later I can change it to whatever value I want. So let's say I want a resistance of 1K. I have got here is 700 ohm, but I can change it to 1 kilo ohm. How? Double click on that particular resistor and I will write 1 small k, and that converts this resistor into a 1 kilo ohm resistor. I can rotate it. I will select and control R. It will rotate it. Then I can connect the terminals in a way we connect it for a half wave rectifier. Okay, so our half wave rectifier circuit is done for us. Now let us see with the help of a voltmeter, not voltmeter, specifically multimeter. I will use the multimeter as a voltmeter. I can use the multimeter for measuring voltage. I can use it for measuring current. I can use it for different purposes. And for resistance also I can use the multimeter. That's why it is called multimeter. So different electrical parameters can be measured by using the same instrument, that is multimeter. So I'm going to use it to measure the voltage. So I will choose the V mode, and I'm interested to know this. When I select this, the multimeter is set to measure the AC voltage. This for AC, this for DC. This is for voltage, this is for current, this is for resistance. So I want to measure AC voltage. So I have chosen AC mode and I have selected the V. So when I will connect it to the source, I have connected it to the input signal. This is my input. Let me change the name also so that you can better relate. Label, this is V input. So there should not be space in between. V in. I have named this voltage source as V in. So since I have selected the voltage measurement in AC mode, if I run this simulation, how much voltage do you expect this voltmeter to show? This is because I am saying voltmeter because this is a multimeter set to get operated in the voltmeter mode. Okay, so how much volts it should show? Tell me, if I simulate this, how much volts, how much AC volts should this show? Tell me. Yes, I want replies. Yes, students, give me the reply. Are you getting the question or not? I have selected this multimeter to work as a voltmeter by selecting V and AC. So it will measure AC voltage, and it will measure the AC voltage of the input, and input is a sinusoidal signal of 1 V peak and 1 kilohertz. How much AC voltage will it show once I run this simulation? Yes, answers.
1 volt.
Ashutosh Khandwal is saying 1 volt. Anybody else who want to reply? Okay, let us see. Let us see how much it shows. I'm running it. Okay, there is some error. I will connect a ground somewhere. Must place some ground reference. Sources, power sources, ground. So I should connect a ground reference. Okay. So this is our reference ground for the source and for the output to be observed. Okay, I'm running the program. So it is showing me 707 millivolt. The AC voltage, it is showing 707 millivolt. Why so?
RMS AC voltage.
Hmm.
RMS AC voltage.
RMS AC voltage. अच्छा कैलकुलेट करना 1 V पीक है तो RMS कितना होगा बताओ इन बाय फॉर्मूला if you know the peak voltage of a sinusoidal source, how do you calculate the RMS value of that particular voltage?
Sir, 1 by root 2.
Okay, so it is V peak is 1, so that's why 1 upon root 2. So 1 by root 2 comes out to be 707 millivolt. Okay, that means this
Sir, multiplying the peak voltage with 0.707.
कौन पहला और फिर पहला ठीक हो जाओ
Sir, multiplying the peak voltage with 0.707.
So listen, if you know V peak, okay, V RMS is simply V peak divided by root 2. In your case, it is V peak is 1 V peak. So 1 upon root 2. So it is coming at 0.707 volt, or you can say 707 point something what millivolt. Okay, so that's why you are getting 0.707 millivolt. Okay, now if I choose DC, this is AC voltage. This is AC voltage of the input source. If I choose DC, how much DC is coming? It is fluctuating between plus 50 to minus 50 microvolt. Can you reason?
Zero.
Yeah, it is to say that the DC is so very less that it is in the range of microvolt. है ना? Microvolt, इतना कम है. So you can assume that it is almost zero, because theoretically we already know that for a pure sinusoid the DC value is 0, but while we are simulating it in our experiment, it is fluctuating in the microvolt range. So it is good to assume that it is in the so less that we can assume it to be 0. Okay. It is fluctuating in between minus 50 to plus 50 microvolt. So this micro range is important, because this, since it is in micro range only, we are saying that it is so less. If it would have been in millivolt or somewhere greater than that, we could not have uh, assumed it to be 0, but it is in microvolt. It is so less. So theoretically, the VDC is 0, that we already know for a sinusoidal signal. Practically, it is so less that it is of least use. So we take it as 0. So why not we should note it all the readings what we are taking. So for the input signal, what we have taken, 1 V peak, 1 kilohertz, for which we found that VAC is coming as 707 millivolt. 707 point something was there. I'm approximately writing it is 707 millivolt. And what VDC it is giving? VDC it is giving how much? It is almost 0. It is almost 0. Not 0, but almost 0. Okay. This is from experiment. These values are from the multisim, simulation. So that's why we are saying it is from the experiment. Whereas VAC is how much theoretically? 1 upon root 2 volt. So it will closely match to the experimental value of VAC. VDC of the input signal, theoretically it is equals to 0. So we are trying to summarize all these values before we proceed. So this is what? Theoretical. Okay, this is expected. This is the measured in the experimental setup. Now, let us go to the multisim. Okay. So we are expecting a rectified output from the across the load. Okay. So let me get rid of this. Okay. Let me keep the multimeter aside and bring an oscilloscope. So I get an oscilloscope over here so that I can get the traces of the signals. The signal at the output, that is across the load. So across the load, whatever I have, I will trace it in channel B. So positive terminal of channel B I have given to this point of the resistor, this terminal of the resistor, and negative terminal of channel B I am connecting it to the reference ground. Okay, that is same as the other terminal of the resistance. On the channel A, I will connect it to the source, the sinusoidal input source. Okay, and negative terminal it is to the reference ground. This is how I have made the connections. So I am expecting a rectified output in the channel B. So if I'll double click on it and run, so I'm getting the signal like this. Somebody wants to enter, I think. Yes, come in. Okay. So this is the signal. I have paused the signal. Okay. If I run the program, it continuously goes. Okay. I'll pause so that I can make some interpretations out of it. So the signal is so small to view. So I will adjust the volt per division reading, volt per division setting. Okay, for channel A, if I'll reduce the volt per division, the signal looks somewhat scaled up. If I reduce the channel B volt per division, that signal also gets scaled up on the oscilloscope screen. But because two signals are there and both are appearing in red, it is hard to distinguish which is from the channel A, which is from the channel B, which is the input signal and which is the output signal. So what I will do to fix this problem, I will change the color of one of those signals. I will stop the simulation. Okay, somebody wants to enter. Okay, they've entered. Okay, so I will change the color of the positive terminal of the channel B, which is to trace the output signal. How will I do it? I will double click on the wire and change the net color to blue. Okay, so net name. Okay, I can do that. So net name. So I will put the net name as V out. Apply. Okay, so V out will appear here in written, and the wire has changed to color blue. So this will have an effect that the signal corresponding to channel B will also appear in blue, in color blue. So I will double click on the oscilloscope, and another thing I can do here is reverse. While I click on reverse, this black background will change to white. Okay, so once I have a white background, it is easier for our eyes to see the things. Okay, so if I run the program, one of the signals will come in blue and another signal will come in red. So obviously we now know here from here that the input signal should appear in red, the output signal should appear in blue.
Sir, not visible
So
clearly.
if
Sir,
I change the y-axis
sir,
of output signal, I can bring it down, and I will change the y-axis of the input signal. I will slightly take it up so that I can clearly I can clearly see the shape of the signals. Now, if I'll reduce the time per division, I will have the time axis somewhat scaled up. टाइम एक्सिस टाइम पर डिवीजन को मैं घटा रहा हूं so that the signal looks spreaded in the x-axis. Okay, so one thing you must remember, while I am changing time per division or volt per division, the characteristic of the signal is not changing. Okay, only thing what I am doing is, by changing the time per division or volt per division, is I am doing a zoom in zoom out process. doing zoom in or doing zoom out, okay, doesn't change the characteristics of the object being observed. Okay, it only changes the way we are able to see the same object. Okay, so that's why you should always keep in mind that time per division change or volt per division changes the way of visualization. It doesn't change the characteristics of the signal. Okay, some people have a misconception that by changing the volt per division you are changing the characteristics of the signal. No, it is not so. We are only changing the way how clearly we can see the signal, the trace of the signal. Okay, anyway, so these are the two signals. The red one is the input signal, the blue one is the rectified output that we are observing across the load resistance R1. Okay, so definitely you'll see here that only the positive half cycles are appearing. Okay, let us set the things to same number of volts per division. So ये 1 वोल्ट पर डिवीजन है, ये भी 1 वोल्ट पर डिवीजन. नाउ इट इज ओके. 1 वोल्ट पर डिवीजन दोनों को चेंज कर दो. So this is the rectified output. So how much is the VDC? How much is the VDC of this rectified output? We can measure it using this multimeter. I will connect it to this output signal. This is to ground. This voltage with reference to the ground. So I will connect it, set it to voltage DC mode. DC voltage it will measure once I simulate. So this is showing the DC voltage that we get for the rectified output is 117.74 millivolt. This is the amount of DC voltage of the rectified output. Okay, that means whatever we are observing here, okay, for the blue output, this is the rectified output of the half wave rectifier. The DC component is of this much measure. The VDC for this rectified output is this much, 117.729. So let us note it down. So VDC. This was the input, characterization of input signals, output signal. For the output signal, that is our rectified signal, the VDC is coming out as how much? 117, I think. 117.729. 117.729 millivolt. Okay, this is from experiment. This is from the experiment that VDC is coming this much. Theoretically, it should be how much? How do we calculate theoretically? The output signal to be is expected as how much? Vm upon pi. This is the expression for VDC for the output signal. Yes or no? Vm upon pi.
Yes, sir.
sir.
निकालो Vm upon pi कितना हो रहा है? Vm we have here is 1 V peak. So theoretical value of VDC is how much, and how much experimentally you are getting this much. So theoretical कितना है निकालो. This is theoretical. This is experimental. Theoretically Vm upon pi. So 1 upon pi. 1 upon pi कितना होता है देखो. Point 318. 0.318. So why are you getting 0.318? Anybody? Hello. Anybody who will reply? VDC, I have by expression it is Vm upon pi. And but experimentally I am getting is 0.117, 0.729. So Vm upon pi, when I calculate it, it gives me 0.318. 0.318. So what is the reason? Vm by pi, what is it? That is 1 upon pi. Array, you have to take into account the drop across this resistance, this diode or not. कितना ड्रॉप हुआ इसका 0.7 ड्रॉप हुआ है. ये कितना होगा फिर. This should be Vm minus VTH divided by pi होगा कि नहीं होगा. 1 minus how much drop is there across the diode when the diode is on.
0.7 volt.
0.7 volt. Okay, इसीलिए तो यहाँ पर भी देखो in the signal you have kept the volt per division almost same. Yeah, same, not almost, it is same. But ये कितना पीक तक जाता है, ये इस छोटा पीक पकड़ता है. Why? Because there has been drop across this resistance. And how much how much drop it has incurred? The drop is equals to the junction potential of this diode, the knee voltage of this diode. And the knee voltage is 0.7 that we have already seen in the diode specification. यहाँ पर हम लोग देखे थे ना. Here, edit model. And here we had already seen the junction potential is 0.7 volt. So this is nothing but the knee voltage, the threshold voltage. So that is why that will make some difference. So 1 minus 0.7. So how much it is? It becomes 0.3.
0.09.
0.09 होता है ना, बाय 5। अच्छा, हमको यहाँ पर कितना मिला, so it is coming 0.09, 0.095 समथिंग मिल रहा है, 0954 ऐसा। So this much of volt, this much of volt. So this is around how much? अगर मिली वोल्ट में लिखेंगे तो ऐसे क्या निकलेगा, 095 मिली वोल्ट, यस और नो, 095.45
Yes, sir.
ऐसा कुछ आ रहा था ना, ऐसे ही कुछ आ रहा है, 45 रिपीटिंग है, 454545 ऐसे रिपीटिंग, जो भी है। तो दिस मच ऑफ मिली वोल्ट, so this is 0.095, so it is close, it is not so ज़्यादा डिफरेंस नहीं है, 0.95 0.95 कितना है, कितना 95.45 millivolt or 117.729 millivolt, so how much difference is there, 17 plus, तो ज़्यादा डिफरेंस नहीं है, this minus this is hardly 10 or 20 of millivolts, है ना। So 117.729 minus 95.45, this is how much, 22 millivolts, the difference is only 22 millivolts, the difference between this experimental and the theoretical value of VDC is only 22 millivolts, that is acceptable, this much of lag between the experimental and the theoretical value. So anyway, so this is we'll note it down, this is VDC experimental, the VDC theoretical, we'll note it down, so it is 0.095.45 millivolt.
volt.
Okay, so volt,
0.95 पर आउट वोल्टेज जोड़े पॉइंट ଦେଇଛନ୍ତି 0.095.45 ଲେଖିଛନ୍ତି।
हाँ हाँ ସେଟା ଏଟା ଭୋଲ୍ଟ ରେ ଥିଲା,
ହଁ ସାର୍ ଏଠି ଯୋଉ ଲେଖିଛନ୍ତି ସାର୍ ଯୋଉ VDC theoretical ଯୋଉ ଲେଖିଛନ୍ତି ସେଠି
हाँ
ପଏଣ୍ଟ ଯୋଡେ ଦିଆଯାଇଛି।
अच्छा अच्छा पॉइंट जोड़ दीजिए, अच्छा ठीक, राइट राइट, so this is straight away 95.45 millivolt, right. Now let us see the VAC measurement. Okay, VAC measurement. So what we have measured is VDC. What we have measured here of the output signal is VDC. Now let us measure the VAC. To see the VAC, I have to choose the AC mode and then run the simulation. So whatever I am getting now, this is the VAC from the experimental. It is coming 177.731 millivolt. So let me write it down. 177 point कितना था, 177.731
731.
731, right, 731 millivolt. So this is what, this is VAC experimental or theoretical, experimental, because we are getting it from the circuit implementation. Okay, can we get the theoretical value of this VAC? कैसे पता चलेगा theoretical value का VAC का? It is not so straight away. Okay. ये ये जो हम लोग किए हैं, so this calculation for the theoretical value of VDC. Similarly, there is no theoretical straight away calculation for VAC. What we can theoretically calculate is I'll change the terminology. VRMS के लिए straight away calculation है. VRMS is what? VM upon root 2, is it? No, this is for only which kind of signals? For pure sinusoids, VRMS is equal to VM upon root 2. It is not for a signal which is a rectified output. So this will not apply. This will not apply. Are you getting or not? हमारा सिग्नल अगर ऐसा होता, AC सिग्नल होता, तो this is okay. VRMS is VM upon root. VRMS is VM upon root 2. लेकिन हमारा सिग्नल ऐसा नहीं है. Our output signal is a rectified output. So this expression doesn't work for this kind of signal. So we cannot write VRMS is equal to VM upon root 2. ऐसा हम लोग नहीं लिख सकते. Are you getting? So how to get
Yes, sir.
VAC? We already know that okay, let us see. Any ideas? बताओ मेरे. आउटपुट सिग्नल का VDC हमको पता है, VAC हमको पता है. हमको एक रिलेशनशिप पता है, that is VRMS square is equals to VAC square plus VDC square. You know it or not? We have already used this expression in our earlier discussion. So from experiment, I have the VDC and I have also the VAC. So experimental value of VRMS can be calculated using this expression. VRMS is equals to, this calculation is for the experimental value. From the experiment we have got this, okay. So experimental value of VRMS we can get VDC square. That means keep in mind this we are doing for experimental. This we are doing for experimental. So VAC we know, VDC we know from the experimental measurement. So VRMS we are not aware. So we are going to check it out. So VRMS square is equals to VAC is 177.731 millivolt square plus VDC is 117.729 millivolt square. तो कितना होगा? अगर हमको VRMS चाहिए तो square root of this whole thing will give me VRMS. मुझे बताओ VRMS कितना है? Calculate it. Calculate it. What is the experimental value of VRMS?
So 213.18.
230.18 millivolt.
The 13 volt. So millivolt. 13 213
213.18
millivolt.
18. So this is how much I am getting the VRMS of the output signal, the rectified signal. Okay. So three parameters of the output rectified signal we have got: the VDC of the rectified signal, the VAC of the rectified signal, and VRMS of the rectified signal. All these are experimental values. So we have got VDC, VAC, and VRMS. Now we can check the performance metric, which are form factor and ripple factor of the rectified output. Okay. So for form factor is defined as VRMS by VDC. Yes or no? So VRMS by VDC. तो VRMS हमको कितना मिला? VRMS हमको मिला 213.18. 213.18 millivolt. And VDC हमको कितना मिला? 117.729. 117.729 millivolt. So tell me how much is the form factor?
1.8.
1.8.
1.81.
1.8. So form factor we are getting it is 1.81, and this is what? This is experimental. This calculation is from the experimental results. So this is the 1.81 form factor is the form factor of the output rectified signal that we are getting from the experimental measurement. So similarly, there is another performance metric called ripple factor. Ripple factor. Ripple factor is given as square root of form factor square minus 1. तो फॉर्म फैक्टर स्क्वायर इसको निकालो कितना हो रहा है? Calculate and tell me.
So 1.5.
1.5. 5. Okay. अच्छा, ये जो हम कैलकुलेट किए, दिस इज एक्सपेरिमेंटल, दिस इज एक्सपेरिमेंटल, experimental, this is experimental, this is also we can say experimental because ये दोनों experimental है और इन दोनों को use करके हम लोग VRMS निकाल रहे हैं, so this VRMS is also experimental. So whatever form factor we have calculated over here, this is the form factor and this is the ripple factor for the experimental setup or for the output of the experimentally implemented rectifier, half wave rectifier. So we should compare it with the theoretical things. So theoretically our VDC was this much. Okay. VRMS हम लोग theoretically कैसे calculate करते हैं for a half wave rectifier? VRMS कैसे निकालते हैं बताओ? VRMS is simply VM upon 2. Yes or no? You have done it in the basic electronics. Theory में तुम लोग पढ़े होगे. We get the VRMS as VM upon 2. If the diode is ideal, अगर ideal नहीं है diode तो VM minus VTH by 2. तो ये कितना हो रहा है देखो. This is a theoretical value of VRMS. VM is 1, VTH is 0.7, 1 minus 0.7 that is 0.3, 0.3 by 2 कितना हो रहा है बताओ.
Zero point 1.5.
0.15, 0.15 volt, right? 0.15 volt. This is VDC theoretical. This is VRMS theoretical. So VDC VRS पता चल गया. VAC निकालने की जरूरत नहीं है. अगर VAC निकालना होता we could have used this expression to get the VAC. तो हम लोग यहाँ पर theoretical form factor और theoretical ripple factor हम लोग निकालने की कोशिश करेंगे. This is experimental. Theoretically, what about theoretical part? Form factor. Theoretically, this VRMS by VDC. So at this point, VRMS and VDC should be the theoretical VRMS and theoretical VDC that we have calculated here. VRMS theoretically it should have been 0.15. 0.15 and VDC how much it should be? ये कितना था हमारा VDC? 0.095 volt. 0.095 volt. So both are in volts. Numerator and denominator both I have kept it in volts. How much it is? Form factor, tell me. Okay. This is what I am.
1.57. 1.57.
1.57. Okay, correct. Then similarly we should go for calculating the ripple factor. Ripple factor. Tell me how much it is. Yes, the formula remains same. So
1.21.
1.21.
1.21. Okay. 1.21. 1.21. So this is from theory. or the mathematical modeling or the theory, it gives me the form factor of this much and this much. But while I implement it experimentally on the experimentally when I implement the circuit for the half wave rectifier, I get an output whose form factor is 1.81 and whose ripple factor is 1.5. Okay. So we'll refer to this all calculation at a later stage when we'll be comparing the half wave rectifier with the full wave rectifier, and then we can compare correspondingly, and we can deduce that which rectifier is better, and how the comparison leads us to this conclusion that full wave rectifier is better than half wave rectifier. Okay. But at this point, you should know that फॉर्म फैक्टर जितना 1 के करीब होगा that is better for us. It is a better rectifier. So we'll expect that form factor जो कि यहाँ 1.8 है experimentally, it will go more close towards 1. Okay, experimental form factor which I have got 1.81, it should get reduced to 1.23 like that. Okay, then only we can say that the other rectifier is better. So the other rectifier which we are going to design is full wave rectifier. So definitely we are hopeful that we get a full wave rectifier whose form factor is more close to the value 1. Similarly, talking about the ripple factor, lesser is the ripple factor, the better rectifier it is. So if I'm getting an experimental ripple factor of 1.5, in the full wave rectifier, I expect the ripple factor to go down a bit more. Okay, it should reduce more. It should be less than 1.5. Then only I can say that the full wave rectifier is a better rectifier than a half wave rectifier. So anyway, I should keep note of this experimental performance matrix, that is form factor and ripple factor, and the theoretical value of the performance matrix, that is form factor and the ripple factor for the half wave rectifier. So now let us move to the full wave rectifier discussion. Are you getting, everybody?
Yes, sir.
Yes, sir.
I will stop this simulation and I will open a new virtual breadboard, blank, create. So this is a new design. Let me name this design. इसको design को name कर देंगे. File, save as. क्या हुआ? Okay, इसको नाम देंगे half wave. अब जो नया बनाएंगे उसको will name full wave. File, save as, full wave. So I'll use the same diode. So I will copy, I'll paste here. So what I'm designing now is a bridge type rectifier. Okay. So I'll require 4 diodes. Control V, Control V, Control V, another Control V. So I do not need to go again and again to place component, get the diodes from there. Okay. I will copy from somewhere and just again make copies of it by Control C and Control V. That I can do in Multisim. So I'll arrange it so that they configure into a bridge type rectifier. How a bridge type rectifier will look like. I need a load resistance also. I should bring a resistance also. control C from here, control V over here. Let it be 1 kilo ohm only. एक मिनट. So does this look like a bridge configuration? So I'll get a source also. Control C, Control V. So tell me, confirm me whether it is a bridge type full wave rectifier. Have I done it right? Hello.
Yes, sir.
Yes, sir.
Okay. So in the positive half cycle, which diodes are on? In the positive half cycle, which two diodes are on?
D4, D3, D3.
Hello.
D4, D3.
D4 and D3, right? In the positive half cycle, this is the path of the current. This is the path of the current. Okay. In the negative half cycle, what is the path of the current? The positive current will flow through this path, through D2, through the load, through the D1, and back to the source. So what I have missed here is a ground. So I will bring a ground. I will paste it here. I will connect it. This. So My circuit is complete. Now, let me get a oscilloscope. Oscilloscope. So to channel A, I will give the input signal. Okay, so positive terminal I have connected to this point because this is the positive end of the our power supply voltage signal, AC voltage source, and negative I will connect it to the reference ground. Channel B I will connect it to the load resistance. Tell me, this positive terminal should be connected to which end? This end or this end? Right or left? Hello?
Right.
बताओ.
The left one. Positive terminal should be connected to the left one.
To the left one. You mean this one? This one?
No, sir, the other side.
This one?
Yes, sir.
How do you decide that?
So the direction of flow of current,
Yes.
considering any one cycle.
In any of the cycles, the direction of current is from right to left. Right to left. So drop will be such that this is at higher potential, this is at lower potential. करंट का डायरेक्शन अगर इधर है तो यहाँ पे ड्रॉप हुआ है रेजिस्टेंस के अक्रॉस में, तो यहाँ पर ज्यादा पोटेंशियल है, यहाँ पे कम पोटेंशियल है. दैट्स व्हाई दिस इज द positive terminal and this is the negative terminal. So this should be connected to here and this should be connected to the this terminal. Okay, is it okay?
Yes, sir.
Run. Before running we already know that we want to see the two signals in different colors, so better I change the color of the wire that goes to the positive terminal of the channel B, that is to plot the output signal, rectified signal. तो मैं ब्लू कर दे रहा हूँ इसको ब्लू किए. ओके किए. Now I'll run the simulation. Wait a minute, I have a call to attend. हेलो. हाँ, कौन बोल रहा है? सॉरी, मैं भी एक क्लास में हूँ. मैं बात नहीं. अभी आप कोई स्कीम के बारे में बताना चाहते हैं? नहीं नहीं नहीं, फ्री अभी फ्री नहीं है. शाम को कीजिए. नहीं नहीं बिजी नहीं चाहिए. थोड़ी आप करते. Okay, anyway, the advertisement call. Okay, so we'll run the simulation. We have run the simulation. Let us see the waveforms. I will reverse so that the background appears in white. I will increase, or I will decrease the volt per division so that it looks scaled up to the same amount. I will also change the volt per division of the channel A. ज़्यादा हो गया. So I will pause the waveform. ये भी ज़्यादा लग रहा है ना. The red one is the input. That means this one. और थोड़ा घटा लेते हैं. So we are anyway going to use the multimeter. So scale being different doesn't make any much of difference because we'll use the multimeter for the measurements. So for visualization sake, I can let the two volt per division scales to be different. That is okay with me. Okay. So y-axis change करेंगे so that I can distinctly see the two waveforms. Input को ऊपर रखते हैं. Input is red. I will take it up and I will take the output signal that appears in blue downwards. Still the x-axis that represents the time axis is so close to view. So I will change the time per division. I will increase it. Sorry, I will decrease it so that it gets better. Okay. Okay. So this is the rectified, full wave rectified signal. Okay. So we can correspond. We have a peak for the positive half cycle. We have a peak at the negative half cycle also. Okay. This is the positive half cycle. This is the peak for the positive half cycle. Here I have a peak. At the output, I have a peak here. For the negative half cycle also, I have a peak. Positive, I have a peak. For the negative, I have a peak. That means I am getting output for both the half cycles, positive as well as negative half cycles. So this is the output of a full wave bridge type rectifier. So this is the visualization part. Now let us go to the matrix, the VRMS, VDC, VAC, those metrics must be found out. So for that I will require a multimeter. I will not calculate the VAC, VDC and VRMS for the input signal because that is same as in the previous experiment because the input signal I have not changed. It is still 1 bpeak 1 kilohertz. So VDC, VRMS and VAC that will remain same. The theoretical this one input signal के लिए VAC, VDC and VRMS all remains same, the experimental as well as theoretical. What will change is the theoretical value and the experimental value of VDC, VRMS and VAC of the output signal that we need to calculate. So let us get a multimeter. I will stop the simulation over here and get a multimeter and I will connect it across the load. So I can connect the positive terminal to this, negative terminal to this because this wire ultimately goes to this terminal. Okay. So positive to this, that means this end, and negative to this terminal. So if I run the simulation, okay, before running, let me set the modes. Voltage AC. AC voltage, it is giving me how much? AC voltage, it is 45.884 millivolt. 45.884. Let me write it down. For the full wave rectifier. So this is the readings for the full wave rectifier. Full wave bridge type rectifier. Okay, full wave bridge type rectifier. So what I got is VAC. VAC, I got it 45.884. 884. This volt or millivolt? It is millivolt. Okay. Millivolt. And this is experimental or theoretical? This is
Experimental.
hello. This is experimental. This is experimental. What about VDC? VDC, I have to select voltage and DC mode, and then again I will run the program, run the simulation. It gives me 41.378 millivolt, 41.392, 49. Let me say 41.378. $41.39. This is millivolt. This is how much? VDC. This is VDC experimental. So I have got the experimental value of VAC and VDC 41.39. Na? How much it is settling to? It is settling to 41.39 only. Okay, 41.39. So I can get the experimental value of VRMS. VRMS is equals to square root of VAC square plus VDC square. बताओ कितना हो रहा है? Calculate.
61.8
61.8.
83.
83 millivolt, right? Millivolt, na? Yes.
Yes, sir.
So this is the full wave bridge type rectifier, VAC, VDC, and VRMS experimental values. Experimental value. Although I am writing it experimental, it has been calculated using the experimental value of VAC and VDC. Directly, I cannot calculate the experimental value of VRMS. Okay. Anyway, so this is the experimental value. What about the theoretical values? I will write in another color so that you can distinguish. The experimental value of VAC for a full wave rectifier is Vm upon root 2 if it is a using ideal diodes. If it is using ideal diodes, then VAC theoretical is Vm upon root 2, but it is not using ideal diodes. It is using practical diodes, which is having some junction potential, some knee voltage is there. So, and how many diodes are on when the diode is operating in any of the half cycle? 2 diodes are operating. Yes or no? So it will become Vm minus 2 times VTH divided by root 2. So how much is VAC theoretical? It is not VAC. Okay. Let me correct. This is what? This is VRMS. Now this is not VAC. This is VRMS. Okay. I got an. मैं यहाँ पे गलती कर रहा था. VRMS. यहाँ पर भी हम लोग जो यहाँ कैलकुलेट किए थे, कहाँ गया इधर? यहाँ पर हम लोग क्या कर रहे हैं? थ्योरेटिकल कैलकुलेट कर रहे हैं. This is VRMS, that is we calculate theoretically Vm minus VTH by 2. Similarly, यहाँ पर VRMS theoretical Vm minus 2 VTH by root 2. How much it is? Tell me. Vm is 1, VTH is 0.7. Calculate करके बताओ. This is experiment.
Sir, negative.
This will be theoretical. बताओ.
Sir, negative আসছে. 0.28 की नेगेटिव अस्सी
हेलो,
अब नेगेटिव अस्सी
अरे नेगेटिव आ रहा है।
सर 2
तो एक काम करते हैं हम लोग, ओके, लेट अस, बिकॉज थ्रेशोल्ड वोल्टेज इज सो मच, आई कैन चेंज, आई शुड चेंज द वी पीक वैल्यू। वी पीक को हम लोग चेंज कर देते हैं, 2 वी पीक कर देते हैं, 2 वी पीक कर देते हैं। 2 वी पीक कर देंगे तो ये भी चेंज हो जाएगा, वी ए सी ये जो मेजर की है, ऑल विल चेंज। ये तुम्हारा क्या है, VDC, VDC विल बी 430.197, 430.2, ओके 430.2, VDC 430.2, 430.2, ये चेंज हो जाएगा 430.2। फोर थर्टी पॉइंट टू मिली वोल्ट, VAC भी चेंज हो जाएगा। इसको हम लोग नेगेटिव होने नहीं दे सकते ना। स्टॉप इट, VAC, run the simulation, 356.25, 356.25, 356. थ्री फिफ्टी सिक्स पॉइंट टू फाइव, VRMS भी चेंज हो जाएगा। दोबारा कैलकुलेट करके बताओ
सर 558.55
कितना हो रहा है।
558.55 558.55
558.55,
55
558.55,
55 55
ओके, तो अभी
मिलीवोल्ट
वी आर, ओके राइट। अच्छा ये फिर यहाँ पे कैलकुलेट करो, यहाँ पे 2 माइनस, this will become 2 minus VTH is 0.7, तो 1.4 हो जाएगा, डिवाइडेड बाय रूट 2,
0.424 फाइनल आंसर।
0.42
424.26 424.26 मिलीवोल्ट 26
मिलीवोल्ट।
0.0 का काट दिया
हाँ कर दो, ठीक है। Now we should go to calculate VDC theoretical, VDC theoretical। अगर आइडियल डेड हो, आइडियल डेड होता है तो क्या होता, 2 VM अपॉन पाई, 2 VM अपॉन पाई होता है, लेकिन ये आइडियल डायोड नहीं है, प्रैक्टिकल डायोड है, तो VM की जगह क्या लिखेंगे, VM माइनस 2 VTH, VM माइनस 2 VTH, विल रिप्लेस VM बाय VM माइनस 2 VTH, ये ब्रैकेट का ध्यान रखना। नाउ यू कैलकुलेट,
0.38 मतलब 381.97 मिलीवोल्ट
51.97
यस
मिली,
मिलीवोल्ट
okay, others should cross check, huh? So this is the VRMS and VDC from theory, this is VAC, VRMS and VDC from the experimental. So let us go for calculating the what, form factor and ripple factor. So form factor From the experiment, it is giving us Vrms by VDC. Vrms by VDC कितना निकलता है बताओ?
1.49 रिपल सॉरी 1.1
1.11 है ना?
11
अच्छा,
यस सर
रिपल फैक्टर
1.49
1.49. You know the formula for ripple factor, no? Form factor square minus 1 plus square root. Okay. Now theoretical one, theoretical का बताओ. Form factor theoretical के लिए
1.11
again 1.11. Okay.
yes sir
That means theoretical and experimental we are getting very close, huh? Form factor ripple factor कितना निकला?
0.48 सर
तो अच्छे से बताओ.
1.4
1 point
सर
ripple factor बोल के चेक करो.
सर जो पहला वाला वो थोड़ा वो पे सर गलत हो गया
बताओ कितना होगा, सही बताओ.
तो 1.29 है फॉर्म फैक्टर पहले का फॉर्म फैक्टर जो ऊपर लिखे हैं हाँ 1.29 फॉर्म फॉर्म फॉर्म
अच्छा
फॉर्म 1.29
29. अच्छा
इस वन सर फॉर्म फैक्टर 1.29 और रिफल फैक्टर है 0.81
1.29. ये कितना है?
0.81
8. ओके. इधर फॉर्म फैक्टर थ्योरेटिकल में
सर 0. फॉर्म फैक्टर 1.11
अच्छा 1.11.
सर रिपल फैक्टर है वो 0.48
1.11 0.48. So these are the different values of form factors, ripple factors, experimental, theoretical for the full wave bridge type rectifier. Let us now compare. That is important. Theoretical पहले चेक करते हैं ना. For half wave rectifier, this one. यहाँ ऊपर लिख देते हैं half wave rectifier. This is half wave rectifier. And this is full wave rectifier. Okay. This is full wave rectifier. This is half wave rectifier. तो जब हम देखते हैं थ्योरेटिकल हम लोग कंपेयर करते हैं थ्योरेटिकल वैल्यूज फॉर फॉर्म फैक्टर एंड रिपल फैक्टर ऑफ द हाफ वेव रेक्टिफायर एंड थ्योरेटिकल वैल्यूज ऑफ फॉर्म फैक्टर एंड रिपल फैक्टर ऑफ द फुल वेव रेक्टिफायर. सो यहाँ पर देखो फॉर्म फैक्टर is 1.57 in the half wave rectifier. 1.57. I told you that form factor will go more close to 1 for a better rectifier. Has it happened? Let us check now. In the theoretical value 1.57 से घट के कहाँ तक आया? 1.11 तक आ गया. Theoretical में 1.57 से 1.11 आया. That means it has come more close to 1. That means full wave bridge type rectifier is a better rectifier than half wave rectifier theoretically. जब हम लोग theoretical comparison कर रहे हैं तो हम लोग बोलेंगे theoretically better है. Okay. Now let us see the ripple factor comparison. Ripple factor theoretically half wave rectifier का 1.21 है. और मैं उस समय बताया था रिपल फैक्टर अगर कमता है तो भी से इट इज अ अगर किसी दूसरे रेक्टिफायर में इस रिपल फैक्टर से कम रिपल फैक्टर है So that rectifier is a better rectifier. तो क्या फुल वेव रेक्टिफायर में रिपल फैक्टर कमा है थियोरेटिकली? यस, कमा है, 0.48 हो गया, जबकि यहाँ पर 1.21 था जो रिपल फैक्टर थियोरेटिकली, that has reduced to 0.48. That means full wave rectifier is a better rectifier theoretically. So we can land up to this conclusion that full wave rectifier is a better rectifier than half wave rectifier by looking onto this form factor comparison, and also by looking into this ripple factor comparison. Okay, both have improved while going from half wave to full wave rectifier. Form factor और ज्यादा 1 के करीब आ गया है, that's why, and ripple factor has reduced remarkably while going from half wave to full wave. यहाँ पर 1.21 था, यहाँ पर 0.48 हुआ है. Okay, these are all about theoretical comparisons and theoretical conclusions. हम experimental observations से हम लोग experimental का conclusion करेंगे. So experimentally देखा जाए, so experimental जो हमारा आउटपुट आया, हाफ वेव रेक्टिफायर का आउटपुट आया, वो फॉर्म फैक्टर इट वाज 1.81. experimentally the half wave rectifier gave a form factor of 1.81. Has it gone more closer to 1 in the case of full wave rectifier? Let us see. It has become 1.29. 1.81 से 1.29 आ गया, so it has gone more closer towards 1. So experimentally भी full wave rectifier is a better rectifier than the half wave rectifier. So can we reach to the same conclusion by comparing the ripple factor also? Let us see. So ripple factor was 1.5 initially, है ना? Half wave initially मतलब in the half wave case. In the half wave rectifier, experimentally we saw that the ripple factor is 1.5. Has it reduced in the case of full wave rectifier? Let us check. 1.5 से घटा क्या? Yes, ripple factor has gone down to 0.81. जो यहाँ पर 1.5 था, यहाँ पर 0.81 हो गया है रिपल फैक्टर. So ripple factor has also gone down by a remarkable amount. So by looking into the ripple factor also, we can say that full wave rectifier is a better rectifier than the half wave rectifier experimentally. Okay, while we are making comparisons on the experimental matrices, we can make experimental conclusions. While we are comparing the theoretical matrices of the half wave and full wave, we can make theoretical conclusions. Are you getting जो मैं बताने की कोशिश किया? Any doubt? Hello? Hello? Hello students, are you getting me or not?
Yes.
So this is all about the ये जो हम लोग अभी हम लोग जो all these values we have calculated, and all the discussion we have made from observation to calculation of the performance matrices to the conclusion that we have made, है ना? ये सारे चीजों को क्या तुम summarize कर सकते हो in the form of a observation table and conclusion? Can you do it? टेबुलेशन करना है ताकि एक ही ग्लिम्स में, एक ही माने झलक में मेरे को पूरा समरी मिल जाए क्या किए हैं एक्सपेरिमेंट में. ऑब्जर्वेशन टेबल तुम ऐसा तैयार कर सकते हो. ओके, दिस काइंड ऑफ टेबुलेशन यू नीड टू डू. ओके, आई एम नॉट डूइंग इट, यू हैव टू डू. ओके, all these calculations, all the observations we have already made, you have only to arrange this in the form of a table. This is for experimental. Similarly, you have to do it for the theoretical. The same table. Input VRMS VDC AC कितना था, आउटपुट का VRMS VDC VAC कितना था, और corresponding form factor. Okay, corresponding form factor. Okay. You will get a value here, here, here. You have to get a value here, here, here. you'll get a value here and here. Okay. For the experimental case, for the theoretical case. Similarly, you will do it for the full wave bridge type rectifier. Can you do it or not? Are you getting? Hello.
Yes, sir.
हाँ. Respond on the chat box. समझ में आया कि नहीं आया? Chat box में reply करो तो. Okay. So you need to do this kind of tabulation. So how many entries you will have? 4 entries. Half wave का experimental entry, half wave का theoretical entry. Similarly, full wave का experimental entry और full wave का theoretical entry. Are you getting or not? I am telling it again. Half wave का experimental के लिए एक रो, theoretical के एक रो, full wave के लिए experimental का एक रो, theoretical का एक रो. You can also make it like this. ऐसे भी तुम कर सकते हो, ज़्यादा आसान पड़ेगा. यहाँ पर तुम लिख देना. यहाँ पे लिख दोगे एक्सपेरिमेंटल, यहाँ पे लिख दोगे थ्योरेटिकल. फिर यहाँ पर ये हो गया तुम्हारा हाफ वेव के लिए. ये तुम्हारा कंप्लीट हो गया हाफ वेव के लिए. सिमिलरली फुल वेव के लिए ऐसे बनाओगे. फुल वेव के लिए फुल वेव में you get a similar table, similar to this table, है ना. इनपुट, आउटपुट, फॉर्म फैक्टर, रिपल फैक्टर. एक एंट्री एक्सपेरिमेंटल के लिए, एक एंट्री थ्योरेटिकल के लिए. And once you have this tabulation, you can make all the analysis and conclusion from directly looking into this table only. You need not have to see the calculation again and again. तुम tabulation को देख के ही you can make the conclusions. You can analyze कौन सा चीज क्या हो रहा है और इसके वजह से what you can conclude. Okay. So you have to make this in your rough copy. You just maintain it from now only.